Have you ever wondered where the future of computing is headed? To answer that, let's journey back to the dawn of computing. It all began in the mid-20th century with classical computing, a technology that harnessed the power of the binary system. This system, comprised of ones and zeros, became the language of machines, and these combinations of ones and zeros, known as bits, became the fundamental building blocks of information. The binary system was a marvel, a revolution that allowed us to transform abstract human thoughts into a language that machines could understand. But as we pushed the boundaries of this system, we started to see its limitations. A significant milestone in the timeline of classical computing was the invention of the transistor in the late 1940s. This tiny electronic device, acting as a switch, could regulate the flow of electricity and thus the flow of information. It marked a turning point, paving the way for the development of complex circuits and, eventually, the microprocessor. The microprocessor, a silicon chip embedded with millions of transistors, became the brain of the computer. It was a monumental achievement that revolutionized the way we process information. But as we continued to miniaturize these transistors to increase processing power, we hit a roadblock. We were approaching the physical limits of how small we could make these devices. It was clear that if we were to continue advancing, we needed a new kind of computing, one that could transcend the physical limitations of classical computing and unlock new possibilities. This realization pushed us to explore the strange and fascinating world of quantum physics. This journey has led us to the brink of a new era, a quantum leap into the future of computing. Welcome to the quantum realm, where the rules of the game change. In the world of classical computing, we've become accustomed to dealing with bits. Imagine these bits as tiny switches that can be either on or off, representing a 1 or a 0. Every tweet, every photo, every piece of data you've ever interacted with on your computer is made up of these bits. But what if I told you there's another layer to this, one that's not binary, but probabilistic? Enter the quantum bit, or qubit. A qubit, like a classical bit, can exist in a state of 1 or 0, but here's where it gets fascinating. It can also exist in any proportion of both states at once. This is thanks to a quantum quirk known as superposition. Imagine a spinning coin. While it's in the air, it's neither heads nor tails, but a blend of both. Only when it lands does it settle on a definite state. That's the essence of a qubit in superposition. It's a bit that's in a state of flux, a blend of 1 and 0, until it's measured. But there's another unique property that sets qubits apart from classical bits. In the quantum world, qubits can be entangled. Think of it like two twins with a mysterious connection. The state of one twin instantly influences the state of the other, no matter the distance between them. This is quantum entanglement. This transition from bits to qubits is what gives quantum computing its immense potential. With qubits, we can process vast amounts of data and solve complex problems much faster than classical computers. That's because, unlike classical bits that work independently, qubits can work together, sharing information and influencing each other. Yet, harnessing the power of qubits is not without its challenges. Quantum computing is at the frontier of technology, where the rules of the game change, and we are still learning to navigate this new realm. As we delve deeper into the quantum world, we encounter two mind-boggling principles: superposition and entanglement. Imagine being in two places at once, or knowing instantly what your twin is doing miles away. Sounds like a science fiction movie, right? Well, not quite. In the quantum world, this is a reality, thanks to the principles of superposition and entanglement. First, let's talk about superposition. This is the idea that a quantum particle, like a qubit, can exist in multiple states at the same time. Picture a coin spinning in mid-air. It's not just heads or tails, but both simultaneously until it lands. That's superposition, and it's what allows quantum computers to process vast amounts of data simultaneously. Now on to entanglement. This is the strange and powerful relationship that can exist between quantum particles. When two particles are entangled, the state of one instantly influences the other, no matter how far apart they are. Imagine having a pair of dice, and no matter how far apart they are, when you roll one, the other always lands on the same number. That's entanglement. and it's what allows quantum computers to process information with incredible speed and efficiency. But why does this matter? In a classical computer, bits can only be in one state at a time, either a 0 or a 1. But qubits, thanks to superposition, can be both at the same time. This means that a quantum computer can process a vast number of possibilities all at once. And with entanglement, we can link qubits together in a way that can't be achieved with classical bits, allowing quantum computers to solve complex problems at a speed that's currently unimaginable with classical computers. These two principles, superposition and entanglement, are the very heart and soul of quantum computing. They're the key to unlocking its immense potential and are the reason why quantum computers have the power to solve problems that are currently beyond our reach. These principles are the secret sauce that gives quantum computing its potential to revolutionize our world. So, what can we do with this quantum superpower? Imagine a world where we can encrypt information so securely that it would take ages for even the most powerful classical computers to crack. This is where quantum computing comes into play. With quantum bits, or qubits, we can create encryption keys that are nearly impossible to break. This is a game changer in the field of cryptography, providing a level of security that's almost unparalleled. But quantum computing doesn't stop there. It's also showing great promise in the realm of drug discovery. In a world where a pandemic can change our lives overnight, the ability to discover new drugs quickly is more important than ever. Quantum computers can analyze molecular structures and predict their behavior much faster than classical computers. This means we could potentially speed up the process of drug discovery, saving countless lives in the process. And let's talk about weather forecasting. Predicting the weather might seem mundane, but it's incredibly complex, and the more accurately we can do it, the more lives and property we can save. Here again, quantum computing can make a huge difference. It can process and analyze massive amounts of data in a fraction of the time it would take classical computers. This could lead to more accurate and faster weather predictions, helping us prepare better for natural disasters. The potential of quantum computing is truly astounding. It holds the promise to solve problems that are currently beyond the reach of classical computers. From optimizing logistical problems to simulating complex quantum phenomena, the possibilities are nearly endless. But just as every coin has two sides, so does quantum computing. It has the power to transform our world in countless ways, but it also poses its own set of challenges. But like all superheroes, quantum computing also has its kryptonite. We'll delve into that in the next scene. Stay tuned. The road to quantum supremacy is not without its potholes. Just like any pioneering technology, quantum computing is grappling with a multitude of challenges. The most significant ones are error correction and stability. The delicate nature of quantum bits, or qubits, means they're extremely sensitive to their environment. Even a slight change in temperature or vibration can cause a qubit to lose its quantum state, a phenomenon known as decoherence. This poses a major hurdle to creating stable, reliable quantum computers. Another hurdle is error correction. In classical computers, if a bit flips from 0 to 1 or vice versa due to an error, it's relatively simple to identify and correct. However, in the quantum world, a qubit can be in multiple states at once thanks to superposition, making error detection and correction a far more complex task. Despite these challenges, the field of quantum computing is buzzing with innovative solutions. Researchers are exploring the use of topological qubits, which are more resistant to errors. Others are developing new algorithms for error correction tailored to the unique properties of qubits. Beyond these immediate hurdles, there's the question of quantum software. We'll need a whole new generation of programmers trained in quantum logic to harness the full potential of these machines. To that end, several institutions and companies are already offering courses in quantum programming. As we peer into the future, the prospect of quantum computing is tantalizing. Imagine a world where drug discovery takes days instead of years, or where complex financial models can be solved in seconds. And while quantum computers won't replace classical ones, they will open up a new realm of computational possibilities. As we stand on the cusp of the quantum era, the future of computing looks exciting and full of possibilities.